Okay, so in this lesson, I want to talk about measuring light, how we measure it and why we measure it and what we can do with that information. In this picture is a very common quantum meter that would be used to measure light intensity in a greenhouse. They're fairly expensive, so not sure it's something you'd want to just run out and buy. So what can we measure? We can measure the intensity, right? So how bright the light is. We can measure what wavelengths of light are available to our crop. And we can measure the duration. How long has the light been hitting our crop? Looking at some units, I think I mentioned these briefly in the previous lesson. Um, Luminance, things like lux, lumens, foot candles are not relevant in horticulture. So discard that information. We're not really, you're not going to see much for that, at least not in a current professional greenhouse context. Global radiance, you will see, and par, you will. So there's a difference between these two measurements, and you'll notice just looking at the units, global radiance could be watts per square meter or joules, and par is always in micromoles. So we're going to dive into that a little deeper. Um, so here, yeah, global radiance is measures joules or watts per square meter. So there's an area associated with it. And then par is just measures only the wavelengths that plants see, is micromoles per square meter per second or micromoles per square meter. Looking at this would be a photometer, which would be something a photographer would use to measure light intensity. That would be lux and foot candles. They follow the response of the human eye, which makes sense because if you're taking a picture, it's a human eye that's going to look at it. But a quantum sensor has a sort of a square notched selection of wavelengths that is controlled with filters in the optics to measure that light as a plant would see it. So the quantum sensor is very accurate in terms of assessing what a plant can use. So PAR stands for photosynthetically active radiation. So PAR. Measured with a light sensor, as I said in the first slide, that blocks out other wavelengths and only the ones that plants can use. PAR meters are usually placed at the level, or what I call the canopy, of the crop. So they're used down low in amongst the crop. It's sort of like a measurement of the final arrival of the train at the final destination, right? So we're measuring the amount of light that's finally filtered through your greenhouse covering, through shade cloths, past heating pipes, structures, shade, curtains, and eventually arrived at your crop. We can use that information to assess how much light the plants have received in a day. That's really important. Or we can use it if we're making decisions about the quality of grow lights, their spectrum, and how much useful light they produce. In this day and age of LED lights, PAR meters have become really important because there's a lot of LED lights on the market that don't necessarily produce really good yields in PAR spectrums. So that's something that is really important. The other thing that these meters can assess is how dispersed is the light in the greenhouse. So if you take a PAR meter and you're moving it around and the numbers are jumping up and down and up and down, you have a really uneven distribution of light. Maybe you got some really hard shadows that you have to deal with, and that's where diffuse light might make a bigger impact on your greenhouse in terms of efficient use of light penetrating deeper into your crop. PAR is a measurement using moles, just like in the chemistry sections of root zone. It's exactly the same thing. A mole is a quantity. It's a unit of measure. It's a counting of pieces. So instead of being, 1 mole is 6 times 10 to the 23 potassium. In the case of PAR, it's 6 times 10 to the 10 to the 23 of photons. So individual elements of light. There are two different types of PAR measurements, and this is important you get this distinguished. There is PPF, which is PAR, where we're measuring photosynthetic photon flux. That is strictly the amount or intensity of light arriving each second. So if you look at the units, it's micromoles per second. Whereas ppfd, or photosynthetic photon flux density, includes a unit of area, 1 meter square. So most often the light meters that are used to assess these are very different. Typically for a photosynthetic photon flux density, a light meter is about 1 meter long. And all the way along the length of it are sensors that individually measure the light. And it's easy for that device to then estimate how much is in a square meter. Where a point source power sensor, like the first one I showed you on the first slide, would give you most often a more accurate micromoles per second unit. You might say, well, what's the difference here? Why do I care? Well, I'll tell you this. If you're buying grow lights or installing grow lights and you want to hang them above your crop and you need to know how many grow lights do I need, how far do I space them, that is where your ppfd plays an important role, because you want uniform light intensity across your crop. You don't want it bright and then dim and then bright. So getting that ppfd is really important for that. So ppf measures intensity and ppfd measures distribution. Next, I want to talk about global radiation. In the earlier slides, I talked about watts per square meter or joules per square meter, or per second per centimeter squared. There's different computer systems use different units, but for the most part, it's reasonably standardized. Global radiation is used by your climate computer system, which you will learn in the winter from Matt. And often there is a weather station that is positioned outside the greenhouse. Ours is on the southeast corner as you walk into the greenhouse. If you look up, you'll see it. And there's a wind direction meter, a temperature meter, a wind strength meter, and this little dome thing is a global radiation meter. And here's your temperature and humidity. And the global radiation meter measures the sunlight. It typically uses something called a pyranometer, which is essentially a solar cell that takes light and converts it into electricity. It's not spectrum specific. It reacts across the entire spectrum of the sun. And that gives you light energy that is impinging at the very top above the greenhouse. Sorry, I said that too many times, I know, but anyway, so global radiation is above the greenhouse, okay? Where typically we put parameters inside at the crop canopy level. So these sensors are called pyranometers. They measure the radiation energy of the sun, right? That includes everything from invisible to visible, not just PAR. It's across the entire spectrum. Some other pictures of climate computer sensors outside the greenhouse. Again, here's your global radiation sensor. This is actually, some people might have thought this was it. This is actually a wet leaf sensor. So it mimics a leaf, and when it rains, it assesses if it's raining or not. Basically, there's alternating wires, and electricity is at the wires. And if a water droplet lands and crosses the two, it conducts electricity, and the computer knows that it's raining. Knowing when it rains is important because then you have to decide if you're going to close the vents to make sure rain doesn't land on your crop. For a lot of crops, it doesn't matter, but for some, you can run the risk of botrytis if you get water droplets on the flowers. Global radiation is something that changes depending on where you are on the Earth. Obviously, the closer you are to the equator, like here it's Miami, you have a lot more light, a lot more radiation. And in Toronto, it's moderate, right? And in Westland, which is a greenhouse region of the Netherlands, it's not as bright. They have a little less light. I think I mentioned that it's a vegetative climate to you in your root zone class. It's not quite as bright as what we see in Toronto. And to be fair, Leamington is actually even brighter than Toronto. That's why there's a concentration of greenhouses there. So your latitude or your position on the globe of Earth is important for influencing how much global radiation you actually receive. For instantaneous global radiation in a greenhouse, we talked about either joules or watts per square meter. There are some modern greenhouses that do use PAR sensors up on the mast, but not many. These units are not so convenient to interconnect, to convert between. But if you have a computer system that uses joules, usually you can kind of get a rough idea of what you're doing to make decisions on whether you have to open vents or turn grow lights on. So a number that is then tied into global radiation is what we call a radiation integral. This is an important unit. Essentially, what it does is it stacks up all the radiation that is accumulated throughout a day and tells the computer how much your crops saw in the past day. So you can either be a radiation integral, which is using your pyranometer or your global radiation sensor, or it can be a light integral, which is using your PAR sensor, using moles versus watts or joules. Again, typically greenhouses are using joules or watts for radiation integrals. But some greenhouses, like there's an orchid greenhouse in Beamsville here called Cosmic Plants, they grow a lot of orchids, and they have PAR sensors throughout their crop that they use to assess their light integral at the actual canopy of the crop, which makes a lot of sense, actually. Especially if you have grow lights on, when you turn them on, it also will add into the daily integral. So it is more useful. But unfortunately, a lot of greenhouses are still in this day and age dealing with just a global radiation sensor. But I think you will see more and more going with PAR sensors at the crops. So a light integral is essentially like a rain gauge in a sense, right? It photons land inside and it accumulates. And when the end of the day comes, it measures how much light arrived at the greenhouse. And that helps you make decisions. Sometimes you don't even have to wait till the end of the day. For example, on a propagation bench, typically you can have the misting either on a clock, every 2 minutes it comes on for 10 seconds. And you can do that all day long, all week long, for the entire year. But the reality is, if you don't have good weather for that, you can either provide insufficient misting, or if it's overcast, cold, and rainy, you may actually soak your cuttings and kill them. So typically, misting on a propagation bench is linked to a light integral. And you might say, well, every time the light integral achieves 1,000 watts per square meter, mist for 10 seconds. And so it will turn the misting on for 10 seconds and reset the light integral count. And then the next time it reaches 1,000 watts, it mists for 10 seconds. If it's a rainy day, you may only mist 5-6 times a day. But if it's a bright, sunny, hot day, you might be misting every 3 minutes, every 5 minutes. That way it's done intelligently. And you can tweak that as a grower with your settings. Another excellent use of global radiation is when to close your shade curtain. Obviously, you don't want to close your shade curtain unless you have to, because as soon as you close that, a lot of light is cut off and your crop's growth rate really slows down. This is one of the reasons why growing crops in the summertime actually is often not nearly as fast as the shoulder seasons like spring and fall. Because it's so hot, you're venting and closing your shade curtains, which means that, first of all, at the high temperature, accelerates respiration, which means your plants can't use all the sugars because a lot of them get burned before they can use them to build something. And second, because you're shading all the time to keep the temperature down, you have less light arriving at the crop, so they actually can make less sugar and they grow slower. Light integrals can also help a computer determine when to turn lights on. So one of the challenges with, say, okay, this is my 24-hour graph, and normally we're expecting a light accumulation of so many watts in a day, right? Let's say it's noon, we've arrived at the middle of the day, but we've actually only achieved X amount of watts. You can have the computer decide, okay, that's it, we're turning the grow lights on, and we're going to make sure we add on some light so that we end up with, at the end of the day, a larger accumulation. So if I was going to plot the light integral for the day, as the light lands on the greenhouse, it starts to accumulate. Remember the rain gauge? And then it's accumulating fast at the middle of the day, and then it slows down. And then as you get towards the end of the day, less light is added and your range gauge is at its max. And that is how much light is accumulated in that day. It looks different than the light intensity graph, because here we're adding, right? We're adding every time more light to the previous amount. Where here we're just plotting the instantaneous light intensity, and then as the sun goes down at the end of the day, it drops. So this doesn't tell us anything about how much light has arrived, where the integral does. I hope that makes sense. Lastly, I have crop growth rates in here. Crop growth rates would be more along the lines of, especially the winter time, where you have sort of growth targets where you're plotting the heights of your crop, and if you're not reaching the height, then you're going to start using your growth rates enhancers, things like temperature, grow lights, nutrients, to try to get your crop to the target height for certain deadlines in your calendar. This is a graph showing what I drew in the last slide. This is the light integral. As the day goes on, you're accumulating light, and then as the day ends, it slows, and you end up with, boom, there's how much light you accumulated in that day. In this case, it looks like, oh, those are instantaneous, I think, actually. I don't know what the total was, but, oh, accumulated, yeah, sorry, here, 2,376 joules. All right, so how much light does a plant need? All right, that's the daily light integral. We just talked about how you plot it, but you need to know how much your light needs, right? So the DLI is the number of photons delivered to a 1 square meter for a full 24-hour photo period. Okay, again, it's in moles because we're talking about units of photons, counting them. So you can convert your global radiation to moles if you have to, watts or joules to moles. And at the end of the day, this will be a big number. Or your computer system may actually calculate it for you, and that is often the case. So here I have a list of different crops. Lettuce requires 17 moles, not micromoles. This is the entire day. Remember, it's accumulating, so micro would be 1,000 times less. 17 moles per square meter per day, whereas tomato needs 20 to 30, peppers need 20 to 30, chrysanthemum, which is a fall growing crop, needs only 15, petunias need about 18, so often bedding plants fall into that category. So you can see right off the bat that tomatoes and peppers are the highest light intensity requiring crops. They need a lot of light in a 24-hour period to grow properly. And interestingly, microgreens and a lot of greens fall into this category of only 10 moles per square meter per day. This is one of the reasons why when you see all these articles on indoor growing facilities, they're growing microgreens or leafy greens, things that are low light requiring, because to ratchet up the light intensity to what it takes to grow something like a tomato or a pepper in an indoor facility costs a lot of money. Just ask anyone growing cannabis indoors how much electricity they go through, and I think you'll find out that they go through quite a bit. And cannabis doesn't need nearly as much light as tomatoes and peppers. It certainly doesn't hurt to have extra light for potency, but technically speaking, doesn't need as much. So this is something often with this indoor growing fad that we read about. They are low light intensity facilities. They struggle to grow anything like strawberries or tomatoes. It can be done, but the economics I don't think are there. You know, your hydro costs, even with LEDs, let's be honest, even with LEDs, it still costs money. And a mole is a mole. If you need 10 moles, you need 10 moles. So doesn't mean there isn't a market for microgreens. For sure there is. So if a DLI for a specific plant is not reached, what happens? What happens if I don't have enough light in a day? Well, first of all, it takes longer to finish the crop. That's not good news. You're trying to make money. Every week or day that it's longer, maybe you miss a shipping date and you can't even sell it. Or if you're growing tomatoes, you get smaller fruit. If you're growing flowers, you get smaller flowers. That's not good. you begin to see things like thinner leaves, right? They're not thin, they're not as dark. And worse yet, thin leaves make it more susceptible to disease. Also, if you don't have enough light, you don't make enough sugar, which makes the plant weaker, which makes you also susceptible to disease. Now, when it comes to DLI, I've got this saying I pulled out from a really important research paper that showed that it is better for a plant to receive low light intensity for a longer time than higher light intensity for a short time. So let's just look at this again. It's better for a plant to receive low light intensity for a longer time than higher light intensity for a short time. A bunch of researchers, this is going back quite a ways, a lot of light research was already done in the 70s and 80s, and now we're sort of kind of redoing it because of LEDs, but for the most part, a lot of it was established. They were growing under different intensities of lights, and especially with a higher intensity, they got up to the point where they're using really high power flashes, where they burst a bright light at the crop, and then there'd be a gap, and then it would burst again. So what they found was that the lower light intensity, as long as they got their DLI, right, for a longer time, did better. And think about it. If a plant has evolved on planet Earth, it's most likely evolved with a 24-hour photoperiod, because that's the cycle for our Earth to orbit around or to rotate on its axis, 24 hours, right? Which means you're going to have an 8-hour dark cycle, typically, depending on the time of year. And that's what plants are expecting. So it shouldn't be that surprising to think that, well, if I just, have a higher intensity, maybe I can get away with shorter time. To some extent you can, but there are some limitations, okay? So I get this question often about light, saying, is there such a thing as too much light? Or what happens if I leave the lights on for 24 hours straight? Plants can handle a fair amount of excess light. That is true. Sometimes you can stress the plant out, and sometimes stressing the plant out has some desirable effects. But what's important, first of all, is if you're going to do that, you need to ramp up the light intensity over some time. If you just hit a plant, boom, really hard, going from regular light to boom, really intense light, and leave it at that, the plant may experience burn. It needs to take time to adjust and accumulate enough proteins like chlorophyll to deal with the added light intensity. Now, looking at from a metabolic perspective, more light drives more sugar production, right? So if you're giving plants lots of light, they're making lots of sugar. And here's a challenge, right? So excess sugar can also stress the plant. When you think about it, the sugars are made in the leaves, right? That's where the chlorophyll is. That's all the green. The sunlight hits the leaves, makes sugars. Now what happens? The sugars have to move from the leaves to areas of growth. In plant science 2, we talked about this, and in plant science 1, I hope you did, the idea of source-sink ratios. So the source is a leaf that's making sugar, and the sink is the fruit or the flower that's the place where the plant is building something. So that's the sink where the sugars have to flow. And a lot of the times I like to use the analogy of a highway, like Highway 401. Let's say the traffic is moving slowly because there's a lot of cars on the highway, and you're on an on-ramp. It's going to take longer to get on the on-ramp, and it's going to take longer to arrive at your off-ramp, and you are going to be late for your appointment. And to some extent, a lot of how sugars flow in plants is a lot like that analogy. In a sense, the best way I can describe it is if, okay, you're on the 401, and there's cars all on the highway, and cars are on all the on-ramps and off-ramps, but they're not moving. They're stopped. Okay? So let's say you go to an off-ramp of the highway. That off-ramp would be the example of a petiole that's attached to a strawberry, or a pedicel attached to a strawberry. So as the strawberry expands and grows, it's going to take some sugars out of that petiole, or take a sugar out of that off-ramp, or take a sugar out of the phloem, right? Remove it and build something with it. And that leaves room in the phloem. And then, of course, that is then quickly occupied by another sugar from behind it. And then you have this whole cascading effect down the highway where the cars inch forward into the new spot that was made available. And if you're a leaf where you're getting sunlight, you're making sugars, you're going to take the sugars you're making and you're going to shove another sugar onto the on-ramp of the highway. So it's actually a really cool system if you can imagine that analogy, because that's precisely how plants can direct sugar in intelligent ways. They can send sugars up, down, sideways, it doesn't matter. Wherever a sugar is being removed from the phloem, it creates an opportunity for more sugars to flow into that location. So you can have sugars flowing down to the roots, up to the top, to the apical meristem, or sideways over to a fruit or a bud. Now, if you are making sugars faster than you can get them on the highway, what ends up happening is you end up with a lot of cars piled on top of each other in the yard or in the parking lot of your leaf. And so then all those sugars that are accumulating in the leaf that don't have a chance to exit in the phloem end up stored in the leaf. And you end up with lots of starch in your leaves, and it changes how your leaves look. They become thick and leathery. And unfortunately, those sugars are absolutely useless to the rest of the plant. Once they're starch crystallized in the leaves of the cells of the leaf, they're no longer available for fruit growth. So you've paid all this money for lights that are making lots of sugars that you can't in fact even use. So this is the conundrum of 24 hours of light. Yes, a lot of plants can handle it. Some can, but most of the time, if they don't have a period of darkness where they can allow the backlog of sugars to flow into areas of need, those sugars end up locked in the leaves. And you may think, oh, my plants, the leaves are nice and dark and thick and lush. That's great. Are you selling leaves or are you selling fruit or flowers? Ask yourself that question. So it is really important to make sure you use light intelligently. And that means knowing what the DLI for your crop is and doing your best to hit it. Another conundrum is that plants actually produce their own sunscreen. It's called zeaxanthin. Zeaxanthin is, most of these types of molecules, or what we call photoprotectants, have a lot of excellent health benefits. And so there's a situation where if you're growing some medicinal plants, having higher photo desensitizers might actually make your plant more useful as from a medicine or medicinal perspective. But from a spending money to make my plant produce better, you may actually be paying all this money for your plant to produce sunscreen, which then blocks the light and it's not even making sugars at that point. So again, it pays to do some research on your crop and know what the DLIs are and what your targets are, and then staying within them. A lot of farms operate with small, narrow margins of profit, and when they turn those grow lights on, they're spending a lot of money. I know at my farm, we had half of it lit, and that was, what, 25,000 square feet, and if you put those lights on for use them for a month in the winter, it cost me about $8,000 or $9,000 in electricity. That's a fair amount of money just for electricity. You had to know you're going to get that value back in your crop. So outdoor light intensity depends on, so now we're looking at outdoor light intensity, right? So going outside the greenhouse and looking at what's impacting how light is impacting my greenhouse. A lot of this is pretty straightforward. Things like clouds. Is it a cloudy day? Is there pollution, right? Maybe there's an altitude effect. If your greenhouse is located at a high altitude, the time of the year, the season makes a big difference. We'll talk about that. And then, of course, the time of day, we know that makes a difference because the sun's height in the sky relative to the time of day. Right off the bat, I want to clarify a couple of things here. A lot of times in class, I ask the question, does anyone know why summer is warmer than winter? And a lot of times people think, well, because of the angle of the earth, we're closer to the sun. But to put things in perspective, if you're sitting in your living room and you go to the far side of the room and you say, okay, my head is the sun, the earth would be the size of a pinhead on the other side of your room. Okay, that's about the scale of the sun to the earth. Now, you tell me, if you take that pinhead and you rotate it 4 degrees off axis, 4 degrees, do you think that's going to make a big difference in the temperature? And the answer is no. The reason is before you on this slide. Because of the angle of the earth and how it's facing the sun, sunlight hits, let's say this is a beam of sunlight. We have the same size beam, and that keeps things constant. This beam is spread over a small area. So we have more energy in a smaller area, making it warmer in the summer. In the winter, this is the same position on the earth, Canada, that energy is spread over a much bigger area, which means there's less thermal energy per unit square meter, which makes it colder. It's all about the tilt, but it's not about the distance. It's about the tilt. Same amount of light spread over a much larger area in the winter. That's why it's cold in the winter. So that little tilt of our axis is pretty amazing, pretty cool. This is another example. You can do this at home. If you take a flashlight and you shine it straight onto a surface, you'll see that it's an intense spot. As you move this flashlight onto an angle so that it's hitting the surface with an oblique angle, you'll see that the surface is bigger, but it's also dimmer. Okay, so this is winter, this is summer. Other things that impact light intensity in the greenhouse. This is an older style greenhouse. There's a lot of arches. We've got pipes. We've got an inflatable tube for moving air. We've got heating pipes. We've got structures all over the place. And those structures all block light and they create shading effects. So quite a few greenhouses, especially the crops that are high light requiring, they absolutely go minimum on anything over top the crop. They try to have larger spaces between the trusses, bigger panes of glass, less support work, less structure, so that more light gets to the crop. Other things that are important, things like dirt. You'd be surprised at how much dirt accumulates on glass. Getting up there and cleaning it sometimes is really important. The depth of the canopy. This is a situation where taller plants versus shorter plants impact how much light penetrates. Looking at the crop to the side here, it's very small. Relative to the greenhouse, this is a very small canopy, so light can easily penetrate into all the leaves and be of use. Whereas with a tall crop, we need to make sure we have light coming from different angles to get deeper into the canopy to make sure that it's all being used to make sugars efficiently. Of course, the angle of the sun and the orientation of the greenhouse, do you run a greenhouse north-south or east-west? Typically, we run it north-south so that the sun arcs across the gutters. The reason being that if this is my gutter, I'll draw a picture of a gutter here. Right, there's my gutter in the greenhouse, a peak, and then there's another gutter. If the sun is shining on the gutter, it's going to cast a shadow, right? This is going to cast a shadow on my crop. And as the sun sweeps right to left, that shadow is going to move across my crop, which means the shadow uniformly impacts my crop across the same sweep. So I spread the loss of light over my canopy. If you run your greenhouse east-west and as the sun scans, the shadow of that gutter scans over the same crop section almost completely, and it ends up you get sections that are smaller and take longer to finish all along your greenhouse because of that gutter. So yes, the orientation of the greenhouse makes a big difference. I hope you followed my drawings there. There's a lot of lines. And then of course, diffuse glass versus clear glass. Do you get diffuse light or do you have direct clear glass? This could also mean if you have a climate where there's a lot of clouds like Holland, you naturally have diffuse light. Where in bright sunny places like California, they're more likely to have direct, no clouds, and harder shade structures or harder shadows on the crops. This is looking at light yields just based on covering materials alone. So glass, which is presumably the best, it's why there's only one S, I don't know. probably because it was a Dutch document, but 60 to 70% of the light makes it through in the summer. That's a lot being lost from reflection and absorption. Double glass, you don't see this very often, but 55 to 60. Single poly, 65 to 70. Not bad. It's almost the same as glass. It's actually maybe marginally better. Double poly, which of course is what you would have in a greenhouse, 50 to 60. So the two that are most relevant here are glass and double poly. So both have decent transmission rates. You might think that glass is not as bad as not as good as you thought it would be, but you know, obviously perpendicular means measuring light coming through when the sun is absolutely perpendicular to the glass, where you get the least amount of reflection. As the sun hits the glass at an angle, it skips some of it off, so you start getting less and less light through. But looking at it from this perspective, you can definitely see that there's a big difference between glass and double poly. So double poly is for lower light intensity crops like cucumbers, where you have the benefit of good insulation and low heat loss. So cucumber can actually grow with 3 or 4 layers of poly, and your energy, your heat costs go down substantially. And then you end up with still good fruit though, because their DLI levels are fairly low. Day length as the year goes on is also a factor. So not just your geographical location, but the time of year. This is a plot for St. Catharines. In December, we're looking at around 9.5 hours of daylight. And in July, we have 15.5. That's a big difference. Good thing most of us are not, good thing. Unfortunately, a lot of us are growing in this time of the year. But technically, a lot of the bedding plant producers in the ornamental world, they plant after December. The big push would be late January, February. Some bedding plants grow so quickly you can put them in March. But so we don't have to grow through the worst time of the year. Growing in December, as you will see this winter, sucks. Like not much happens. Everything kind of just looks at you like, well, look, we just maintain enough sugar to stay alive here. As soon as you get to January, though, things really start to take off, and it's exciting to see. The other thing is we've got light intensity throughout the day length. We've got your position on the planet, which dictates the angle of the sun. The other thing is the amount of light that the plants see throughout the day is a bit different than our eyes. And here we have sunset, and here we have sunrise. And obviously after sunset, going this way, light intensity is still registering, but the plants don't really see it anymore. So it's not a very useful time. If anything, it's that far red time I talked about, which can cause plant stretch. So this is not necessarily desirable. And of course, in the morning, plants take a long time before they wake up, before they actually see something. I've seen some papers that show that until the plants see blue light in the spectrum, not much happens. It seems to me that blue light actually wakes up the photosynthetic apparatus. And you don't see much blue early on. The sunrise in the morning is orangey yellow, right? And then the blue, it becomes more of a daylight spectrum. And then the plants sort of wake up. So what's the takeaway? So wavelength affects energy. From the previous lesson, we talked about that. UV being high energy wavelengths that burn, and red being sort of lower energy. We talked about how light bends and scatters, and how that's interesting in the greenhouse in terms of getting through the different layers, and also how diffusion can be beneficial sometimes. And things like condensation can affect how much light passes through glass. We've looked at DLIs today, daily light integrals, and minimum light levels that impact quality, and we use that to determine when to turn on grow lights to make sure our crops are getting their DLI. It's like you getting enough calories to survive your day with all this online learning. And then lastly, we talked about light intensity with global radiance and PAR. So remember, global radiance is measured outside the greenhouse, above it in the climate tower. And PAR is typically measured at the canopy and measures only the wavelengths that plants see. I'll say this, that PAR meters typically were very expensive and exotic, and they were not seen much in greenhouses, but they have come down in price such that a lot of greenhouses are actually installing PAR sensors and hooking them up to your climate computer, and you see less global radiance reliance. But for now, it's good to know the difference, and global radiance is still useful for turning on things like shade, when to turn on grow lights, all that sort of stuff. But PAR ultimately trumps the joules watt meters in the sense that it's giving you real data on what plants actually are seeing. Things that will affect seedlings, or being intelligent about when you turn the grow lights on so that you're not wasting electricity. So, well, I hope that was useful. I hope you found it interesting. All right. Talk to you later. Bye.